Hello, this is Ted Miller speaking, and I'm honored to have a chance to talk about my working relationship with Hamish Small, a wonderful man who made my career everything that it was. Yeah, we worked together only 5 years, from 1979 to 1983, and during that time, we enjoyed the collaboration on things like the flow meter you'll hear more about, and indirect photometric chromatography, and just being friends in general. I'd like to clarify that Hamish hired into Central Research at Dow in 1955, whereas I started in really an engineering function within the division, designing and implementing process analyzers. Of course, Hamish's influence in developing not just ion chromatography, but ion exclusion, other ion exchange methodologies, uh, influenced my agenda online, where we wanted to implement process analyzers for difficult problems tractable only by Hamish's new ideas. So I admired him from afar by working in an engineering function, again, within the division, all located within Midland, Michigan, along with the analytical sciences function um, that housed people like Tim Stevens, who played an important role, as you'll see. Now, Hamish enjoyed the environment of non analytical central research because he had resources, as you just saw, who helped him develop technologies essential to ion chromatography, molecular resins, low capacity anion exchangers, and so on, as you just saw. Meanwhile, as I said, I was tasked with the responsibility of designing and implementing process analyzers using Hamish's techniques. And it's not a simple task because 24/7 online, meaning that the analyzers communicated with process control computers, meant the responsibility for them was very high. So, as I did that job in the first 5 years of my career, I ended up publishing a chapter on the subject, just common sense in terms of analyzer implementation. And I excerpt from that many slides and figures that you'll see in this talk. And again, it'll emphasize Hamish's influence in central research, generating in particular ion chromatography with its many applications in processing, including power production, where trace anions in particular are critical to the survivability of these massive production plants. So Hamish's recipe again for doing ion chromatography was essential to the design of the instruments, which is not simple because the support reagents, sample handling, replicate injections all had to be managed properly within the device. But again, from afar, I was admiring Hamish's creativity and his work environment because the engineering responsibility was to make these things work online, as opposed to having fun with the method development side of it. This is a look at a chromatogram, which might be not too impressive from a theoretical plate point of view. I'm certain it's not. But remember, this is 40 years ago or more, where plate count was not as important as the durability of the instrument. So you want a good, rugged separation technique that's not influenced too much by environmental conditions. Another of Hamish's developments was to look for trace weak acids in waste brine. Now we're talking 15-20% sodium chloride brine and other inorganics. So measuring trace 10 to 100 ppm of various weak acids was a challenging problem. We had to first strip out the sodium chloride using silver precipitation. And again, you'll see at the end that you can go to references for more details of what's going on in the figure. What I'd like to emphasize is Hamish's creativity. Here again, ion exchange was a way of getting at TDS, or total dissolved solids, in a way that was physically normalizing of the different conductivities of the ingredients of the brine by exchanging them all to common ions and then detecting them online. So as I said, um, while doing that, I couldn't help but become more aware of Hamish's reputation, not just in Midland or the state of Michigan, but even throughout the country and globally. And Another project that I did in the division is notice that analyzers for caustic concentration in scrubbers of acid gases used a cumbersome technique. Can you imagine automating like a washing machine the titration process with endpoint detection based on slope, which had to be done in analog circuitry back in the ancient times when this all occurred? So one type of analyzer I installed was the process titrator. So getting to know more about ion exchange led me to think, why not do something simpler and exchange the base to water non-conductively. And these dramatic high concentrations then of base could be measured by conductivity, and then by subtracting the high conductivity of the acid or base conversely, one could by difference determine online the concentration of base. And in fact, it works. And Tim and I collaborated on the details of implementing the chemistry, and we ended up patenting it. But again, it got me able to talk more and get to know Hamish and his great creativity. And a theme that I'm going to come up with here is Hamish always had a topper. Socially, such an engaging guy, because under any circumstance, he was that quiet guy in the room to begin with who ended up being the dominant figure because of his cleverness, sense of humor, and creativity on a technical level. So that certainly happened here because Tim and I were very proud of differential conductivity ion exchange, and I just explained how it worked. And again, the process analyzer needed to recognize all these issues, but that's why simplicity was so essential in the design as opposed to, titration and the mixing and endpoint detection. So then when I ended up joining Hamish in 1979, he commented, well, your technique's pretty cool, but why not take advantage of the 14.7 kilocalories per mole heat of neutralization and measure temperature instead using an acid form resin to encase, if you will, 2.6 milliequivalents per mil of acid in a stationary form. So if you inject base into a stationary small cartridge of acid form resin, you elute a very sizable tens of degrees C thermal pulses. And again, Hamish always had a topper. This was his idea, and it ended up supplanting what Tim and I had proposed earlier. So again, collaborative projects like this with Hamish led me to finally make a case to Dow management to let me make this huge transition from the operating division of Dow in Midland to Central Research, which was a wonderful playground because the goal was to develop new products by setting the agenda yourself as opposed to being dictated to by the management of the plant who had budgets to solve very specific problems. So it was just a joy to associate with Hamish instead in a blue sky basis. Hamish always had a topper. As I said, this thermometric ion exchange, as we called it, is really a physically vastly superior way of quantifying acid or base by using base or acid, respectively, ion exchange resin followed by temperature detection. But then Hamish and I were distracted by other things and looking for new opportunities. He had done hydrodynamic chromatography work in the past based on fluid dynamics. And I have to return to a past project that I did in the division that'll help explain how Hamish and I moved forward on this thermal pulse flow injection metering technique. And it goes this way. One of my assignments in the division was to measure trace phenolics, okay? Trace phenolics in waste brine. Again, parts per million in high levels of brine. So the way we did it, we realized the UV absorption at 260 nanometers was a very promising way to measure the various organics, the phenolics rather. But we had the problem of the background brine, which was a nuisance, and in particular the iron contained in the brine. Iron absorbs broadly in the UV, and it ended up being a disabling interference in terms of the measurement. So our idea was to acidify the sample all the time and therefore protonate all the phenolics so that they would be in the vapor phase if you strip them out continuously. Can you imagine? Boiling the sample constantly and then measuring the ratio of condensate, which contained all the phenolics, and the bottoms contained the waste brine. But you had to know the flow rate ratio in order to calculate the phenolic concentration. You need to know the concentration factor in the distillation process. So I used the siphon dump assembly that you saw earlier, which was not patented, but it's necessary to measure the frequency of emptying, spontaneous emptying of the siphon dumper. So I worked with the thermistor at that time and developed the circuitry to make that simple detection interface to the plant control computer. So Hamish, aware of that work, said, well, let's think about other ways that thermistors in a self-heating mode could be used to do a challenging problem like measuring cc a minute flow rates. And that led us to this development of a flow injection method where 100 milliwatts upstream, you need two different thermistors. One is 10 times bigger in diameter, 100 times bigger in volume, that generates 100 milliwatts on a half a second pulse. Downstream, you measure with a much smaller thermistor that is merely a temperature sensor. You measure not the arrival of the temperature zone because there can be vast interference upsetting the quality of that detection. It's the second time derivative of the temperature pattern with time. And that ended up being the key idea because without the differentiation, ambient fluctuations in temperature upset the measurement. Using this technique, it in situ measured the centrally injected pulse with high accuracy, and the calibration's very good. 0.1% is the precision and accuracy on that level as well. Copious data is available in the references to show that that's true, but it's amazing that this thermal generation technique on a pulse basis did the job. The prior art search disclosed other techniques using thermal injection time of flight, but none of them was able to recover in time that the dead time is minimized. Think about it, as the flow rate changes, the transit time varies. If you have a dynamic range in the flow meter, you have to have the recovery as short as possible, the ideal thing being that the detection event triggers a new upstream pulse. And in fact, the differentiation technique made it possible to do it that way. Now think about it. Back in those days, we didn't have embedded computers in products, so I had to develop analog circuitry that did the math, and it was possible using operational amplifiers, of course. It found use within Dow. The licensing strategy at Dow was to ask us, did you sell 100 prototypes within Dow? If so, let's talk about the generic utility of it outside. And in the case of flow meter, we did just that. We had a more elementary operating version of it that we packaged and sold in the 100-unit kind of quantity. The market inside of Dow was, in particular, gel permeation chromatography, because the assignment of molecular weight range is strictly dependent on elution volume as opposed to speciation, as is normally true in chromatography. So GPC users really found great utility, and we published a paper showing that if you deliberately change the pump setting in size exclusion chromatography, aka GPC, if you deliberately change the pump setting 10%, there was less than a 1% offset in the molecular weight determination, which is really amazing. In other words, it forgave serious pump fluctuations in terms of the assignment of molecular weight range. So a side story, later after Hamish's retirement, we exploited the fact that the centrally detectable pulse reveals the rheology of the sample, because in laminar flow, Newtonian fluids exhibit a parabolic distribution of flow, very strictly so. But if you have non-Newtonian behavior, that the shape is no longer a parabola. So by measuring the centrally injected pulse, we were able to reveal the non-Newtonian nature of the sample. Now, of course, ion indirect photometric chromatography was just a joy. And Hamish really came to me one day and said, how about this idea? But Ted, I need your help with doing the first cation work and telling me how to optimize sensitivity, because remember now, you're using a photometer on purpose at elevated attenuation. So where's the sweet spot in terms of optimizing the baseline absorbance and yet letting signal strength be high? And in our publication, Indirect Photometric Chromatography, I talk about that aspect of things. And it boils down to essentially operating between 0.5 and 0.6 AU. That's the sweet spot in terms of sensitivity. At least that's what we saw at that time. Again, after Hamish's retirement, I tried to continue his kind of innovation within research, and this is a publication that talks about how to simultaneously detect anions and cations. If you happen to have a detector that's simultaneous dual wavelength, where you have the math of the ratio of absorbance settable and calculable in the detector, it's possible to elicit simultaneously two different chromatograms in a single flow cell. And again, references are available at the end of the talk so you can see more about this. The problem is it requires copper orthosulfobenzoate is a very unique reagent, the only one we were able to find, eluent rather, that was able to do this, because you can't mask anion or cation eluent ion with the eluent itself. So again, we're just so fortunate to have that time together, and Hamish, as an associate and a delightful friend, was just such a joy, and we remained in frequent contact by email really until his passing last year. And among the emails that he sent was a statement of his going north where he lived to look at an airplane that was the same type that had brought him to America in the mid-50s. Here's an example again of his sense of humor and self-deprecating personality. But back to the airplane. So last year he sent me a picture of him posing with family members, Beryl and his daughter Deb, at the same airplane in a museum that had brought him to the States. So it's very interesting that he has a sense of history. He's a wonderful watercolor artist. So many aptitudes beyond science. Just what a privilege to have known him. But again, he always had a twist in a social situation, or technically, he was the guy who ruled the roost, had the best insight or the most humor and the most engaging to be with. Now, here's his narrative to me about the airplane. And I couldn't help but jibe him a little bit and ask, well, why don't you just hop on that same airplane but travel in the opposite direction, and maybe you'll go back in time and you'll be a young man again and the whole adventure can begin one more time. But his answer you see here was, well, you know what, Ted, I'm pretty happy with how things turned out. The understatement of all time. Well, thanks for your attention. And at the end, I show my email, how you can contact me. And I really appreciate the privilege of having a chance to talk about my greatest hero. Thank you.